Section 15.1. Motion of an object attached to a spring. In this session, we will explore the fundamental concepts of oscillatory motion. Our outline includes the simple harmonic motion model, understanding Hooke's law and the nature of restoring forces, and analyzing acceleration within this framework. We will also look at the mathematical representation of these systems and compare how the physics applies to both vertical and horizontal springs. To begin our introduction to oscillatory motion, it is important to recognize that these movements serve as the essential basis for understanding all types of waves, including mechanical and electromagnetic waves. A standard model used to study this is a block, with a specific mass attached to a spring, resting on a horizontal surface that is frictionless. We define the equilibrium position as the point where the spring is in its natural state, neither stretched nor compressed. If we disturb the block from this position, the system will begin to oscillate, moving back and forth around that central equilibrium point. The physics of this movement is governed by a restoring force and Hooke's law. When the block is displaced to a certain position, the spring exerts a force that is directly proportional to that displacement. According to Hooke's law, the spring force equals the negative of the spring constant multiplied by the displacement. We call this a restoring force because it is always directed toward the equilibrium position. Essentially, the force acts in the opposite direction of the displacement, always trying to pull or push the mass back to the center. We can visualize this spring mass system through three different states. First, when the displacement is to the right, making the position positive, the spring force acts to the left. Second, when the block is exactly at the equilibrium position, the displacement is zero, and therefore the force is also zero. Finally, when the block is displaced to the left, resulting in a negative position, the spring force acts to the right. These diagrams illustrate how the force vector always points back toward the center, regardless of which way the block has been moved. By applying Newton's second law, which states that the sum of forces equals mass times acceleration, we can determine the acceleration in simple harmonic motion. Substituting the spring force into this equation shows that the acceleration equals the negative of the spring constant divided by the mass, all multiplied by the positions. This tells us that acceleration is proportional to the position and directed opposite to the displacement. A key point to remember is that acceleration in simple harmonic motion is not constant. It varies continuously as the position of the block changes. Looking at the dynamics of this motion, if the block is released from a maximum displacement called A, the initial acceleration is the negative of the spring constant times A divided by the mass. As the block passes through the equilibrium position, where the displacement is zero, the acceleration becomes zero, and the speed reaches its maximum value. When the block reaches the opposite end at negative A, the acceleration is positive, and the speed returns to zero. In an ideal system without friction, the block will continue to oscillate between these two turning points indefinitely. The principles we have discussed for horizontal springs apply to vertical springs as well, with one primary exception. In a vertical setup, the weight of the hanging block causes the spring to extend initially due to gravity. However, if we define the new resting position of the block on this extended spring as the zero point or equilibrium, all the standard equations for simple harmonic motion remain perfectly valid. This allows us to use the same mathematical framework for both orientations. To develop a mathematical representation of this motion, we express acceleration as the second derivative of position with respect to time. This gives us a differential equation where the second derivative of position equals negative k over m times the position. To simplify this, we denote the ratio of the spring constant to the mass as omega squared. This results in the final differential equation where the second derivative of position equals negative omega squared times the position. We are looking for a function that, when derived twice, returns the negative of itself multiplied by a constant. The solution for the position of the particle involves trigonometric functions. Both sine and cosine satisfy the differential equation we just derived. A general solution for position as a function of time is given as position equals the amplitude a multiplied by the cosine of the quantity omega times time plus the phase constant phi. From this, we can find the velocity by taking the first derivative, which is negative omega times the amplitude times the sine of the quantity omega times time plus phi. The acceleration is the second derivative, resulting in negative omega squared times the amplitude times the cosine of the same quantity. In summary, simple harmonic motion occurs whenever a restoring force is proportional to the displacement. The acceleration is always directed toward the equilibrium position and can be calculated as negative k over m times the displacement. The system will oscillate back and forth between the positive and negative values of the amplitude. Finally, we can accurately model the position of any particle undergoing this type of motion using a cosine function that incorporates the amplitude, angular frequency, and phase. To conclude, let us consider two review questions. First, if a block on a spring is pulled to position A and released, what is the total distance it travels in one full cycle? Think about the path from the starting point to the opposite side and back. Second, why are the standard kinematic equations for constant acceleration that you learned previously not applicable here? Consider the relationship between acceleration and position that we discussed today.